So our last type of structure are covalent substances, but when we look at the flow chart, if I scroll back, we can see that for covalent substances we've got two types, simple molecular and macromolecular, one of which has weak forces, and we've got three different types of forces that we've looked at, and one of which has strong covalent bonds. Okay, so we've got two different things to consider. So if we just go back to covalent substances, so we've got two types. We can either be macromolecular or simple molecular. We're going to look at each one in turn. We're going to look at simple molecular first. So the properties of the molecular covalent substances, the simple molecular substances. So they exist, these are things that exist as single molecules. So we're talking elements that are molecular, like iodine and sulfur and phosphorus, and all the other diatomic ones, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Things like methane, things like water, things like ammonia, things like HCl gas. These are simple molecular substances. So their structure is simple molecular. This one's a little bit more confusing because their bonding is covalent, but their forces are not covalent bonds. Their forces are weak intermolecular forces, and we will have to pick which one between the molecules. Not between ions, not between ions and electrons, not between atoms, between molecules. So this is an example of, say, something like iodine, a diatomic molecule. So these are the molecules, okay, these little things. And this bit here, that would be the covalent bond holding the atoms in the molecule together. So if you imagine this was iodine, II, this would be the covalent bond here, the shared pair. What is there holding them in this lattice structure? What force is holding one near to the other? Well, it's a very weak force of attraction between these molecules. So they tend to have low melting points. So low melting points because not much energy is needed to overcome, so we don't break bonds here, we overcome weak, and then you're going to put in a type of force, but that kind of a little star there, attraction between the molecules. So you're going to need to determine whether the force is, for each molecule that you're given, is it van der Waals? Is it a non-polar molecule? Is it permanent dipole-dipole between those polar molecules? Or is it hydrogen bonding? So you'll need to decide which one of those three. So one of those three is going on this line. Are you putting van der Waals? Are you putting permanent dipole-dipole? Or are you writing hydrogen bonding? But whichever one you're picking, it's a weak force, and so you don't need very much energy. If something had hydrogen, was a similar size and had hydrogen bonding, and something else had van der Waals, then yes, the hydrogen bonding one would be a bit stronger, but it would still be weak in comparison to, say, an ionic bond. So it depends on the question how you would answer. Solubility. Well, these things generally insoluble in water. unless they can form hydrogen bonds to water. So the ones that can do hydrogen bonding tend to be more likely to be soluble. They do not conduct electricity. No free ions because they're not ionic. And no delocalized electrons. All their electrons are involved in bonding. So do not conduct. So now what we're going to do is look at the macromolecular substances, the giant covalent substances, graphite, diamond and graphene. But so as well as these three, there's also, and it would have exactly the same properties, silicon and silicon dioxide as well. So it would have the same properties. What's our structure here? Well, our structure is macromolecular. Our bonding is covalent and our forces are many strong covalent bonds. And what are they between here? Here they're between atoms. Okay, now all three of these things have high melting points. So I'm going to write across all of the table at once. Why do they all have high melting points? Because it takes a lot of energy to overcome the many strong covalent bonds between the atoms. Then it says that diamond does not conduct, but graphite and graphene do conduct. That is because in diamond the electrons are fixed in bonds and cannot move. So they cannot carry current. Whereas in these two, graphite and graphene, each carbon only makes 3 bonds, 3 covalent bonds. So 1 electron is not used. Remember, carbon has 4 outer shell electrons in bonding and is delocalized. Free to move and carry charge. And then they're all insoluble in water because it would require many strong covalent bonds to be broken so they do not dissolve.